Well, okay, so why don't we start? Our speaker is Ajmain Jamin, who came to the Graduate Center by way of Stony Brook and Bronx High School of Science. So let me just
Okay.
a couple more people here. And you can begin.
Okay. So yes, my name is Ajmain, and I am talking about complete regular dessins of genus 1. So that's the title of my talk, and this is a project that I've been working on. So I'll try to explain it today. Okay, so um, the goal of my talk is to explain these two pictures and basically tell you why they're the same picture. Okay, so my talk is split into three parts. In the first part, I will be talking about complete regular maps, which is a notion in topological graph theory. And then I'll move over to dessins and Riemann surfaces. And in the final part of my talk, I'll talk about the algebraic side of Riemann surfaces. So first of all, what is a complete regular map? So first, we have surfaces. So I have some conventions and notations that I'll be using in this talk. All surfaces in this talk are assumed to be closed, connected, compact, and oriented. So as such, a surface is uniquely determined by its genus, and the notation sigma g denotes the surface of genus G. So sigma 0 is the sphere, sigma 1 is the torus, sigma 2 is a two-hole torus, and sigma 3 is the genus 3 surface. And a map on a surface is an embedding of a graph into a surface such that the complement of the image is a disjoint union of topological disks. So here on the left, we have a map on the torus, and the underlying surface of this map is just the genus 1 surface, the torus, but it also has these vertices, edges, and faces. And those are coming from an embedded graph. So here you have these edges, and these vertices are the edges and vertices of a graph embedded inside of the torus. And it's a map because the complement of the image of this graph is a union of topological disks. So each of these faces is one disk. On the right, this cone is not a map because first of all, you need to have an underlying surface and an underlying graph. So the cone can be considered as a sphere. Its underlying surface is a sphere, but what would the underlying graph be? In this picture over here, you have one vertex. So let me try to draw here. So we have one vertex over here, and then we have an edge over here. But this is not really a graph because in a graph, you need edges going between vertices. Yeah. And so this circle here is not an edge that's connecting two vertices. So in that sense, it doesn't really have an underlying graph. And even if I did put in a new vertex here to make it have an underlying graph, the complement of the image of this graph inside of the sphere does not break up into a union of topological disks. You see this connected component of the complement is looking like an annulus, which is not a topological disk. So that's why the picture on the right is not an example of a map. Okay, so we have the notion of maps, and now Platonic solids are maps on the sphere. So Platonic solids have an underlying graph. So for example, the tetrahedron has this graph with 4 vertices and however many edges. And then you can embed these graphs into the sphere, and that will be an example of a map. And each of these, each of the connected components of the image, complement of the image consists of topological disks. So that in that sense, Platonic solids are maps in the sphere. Now, another piece of notation is, or another notion we're going to use is the notion of a complete graph. A complete graph is a graph where every vertex is connected to every other vertex of the graph via exactly one edge. So the notation Kn denotes the complete graph with n vertices. So we have K4, K5, K6, and K7. These are all complete graphs. And a complete map is an embedding of a complete graph into a surface such that the complement of the image is a disjoint union of topological disks. So the notation Kn embedded inside of sigma g denotes a complete map with underlying graph Kn and underlying surface sigma g. So the tetrahedron that we saw in the slide about Platonic solids is an example of a complete map because the underlying graph is a complete graph on 4 vertices and it's being embedded inside of the sphere. So we would denote this tetrahedron as a complete map as K4 embedded inside of the sphere, sigma 1, sigma 0. So in any map, you get a partition of the underlying surface into vertices, edges, and faces. And so, for example, the cube here, we know what vertices, edges, and faces are for the cube. They're just vertices, edges, and faces as we normally know them. But a map is a topological notion. So, for example, on the torus, this map has curved edges and curved faces, and that's also valid. So this, maps can have curved edges and faces as well. So now there's this fourth notion, vertices, edges, faces, and flags. So first I need to say, what is an incidence? A vertex, edge, or face is incident with another vertex, edge, or face if the former intersects the boundary of the latter. So in this picture here, the labeled vertex, edge, and face are all incident with each other, because the vertex is on the boundary of the face and the vertex is on the boundary of the edge and the edge is on the boundary of the face, right? So they're all incident with each other. And a flag is a mutually incident vertex, edge, face triple. So in this picture, this vertex, edge, face triple is a flag because they're all mutually incident. And the reason we call them flags is because if you consider a vertex, an edge, and a face, it looks like a flag, right? So, so that's the notion of a flag. And for any map, you have a bunch of flags on your surface. And then what does it mean to be a regular map? So regularity is a symmetry condition. A regular map is a generalization of a regular polyhedra. Regular maps exhibit a large number of symmetries. So remember I said these regular, the Platonic solids are examples of maps on the sphere. And in general, any polyhedron is also giving you an example of a map on some genus G surface. And we have a notion of regular polyhedra and irregular polyhedra. And the regular polyhedra are the ones that have a lot of symmetries, while the irregular polyhedra don't necessarily. So regular polyhedra are going to be examples of regular maps, while irregular polyhedra probably most likely aren't going to be regular maps. So an automorphism of a map is what we mean rigorously by a symmetry of the map. An automorphism of a map is a self-homeomorphism of the underlying surface that preserves the map structure. So it sends vertices to vertices, edges to edges, and faces to faces. So in the example of the tetrahedron, which is a complete map on the sphere, we have a bunch of rotational symmetries and reflectional symmetries. If you consider the tetrahedron not as a topological object, but as a rigid geometric solid in 3-dimensional space, you can imagine the rotations about various axes and the reflections in various planes. And these geometric symmetries are also automorphisms of the map. So as in they are self-homeomorphisms of the underlying surface that preserve the map structure. So an automorphism of a map is a generalization of these symmetries of geometric objects. So it's a topological notion. And also we have that the rotational symmetries of the tetrahedron are orientation preserving automorphisms, while reflectional symmetries are orientation reversing automorphisms. So now I can finally get to what is a regular map. A regular map is a map that exhibits the maximal amount of symmetry. So the automorphism group acts transitively on flags. So this means that for any two flags of the map, there exists an automorphism of the map sending one to the other. So regular polyhedra are going to be examples of regular maps. And specifically, the tetrahedron is a regular map. Can you see why? So again, what it means to be a regular map is that you can send any flag to any other flag. So for example, I have maybe this flag on my tetrahedron, and I can send it to this flag also on my tetrahedron just by doing a rotation about this axis, right? And for any two pairs of flags that I choose on my tetrahedron, there exists some automorphism of the map that sends the first flag to the second. That's why it's a regular map. So that's what regularity means. And I'm interested in complete regular maps. So the tetrahedron is both complete and regular. It's complete because it's an embedding of a complete graph into a sphere, and it's regular because the automorphism group acts transitively on flags. So are there other complete regular maps? And so this is the first question, and it's actually has been answered a long time ago, but I'll get to that. So one fact about complete regular maps is that the group of orientation preserving automorphisms of a complete regular map has order n times n minus 1, where n is the number of vertices of the underlying complete graph. In other words, we can write the orientation preserving automorphism group as plus of m, where m is the map. And this group has order n times n minus 1. So for the tetrahedron, if this fact is true and you believe it, the tetrahedron should have 12, which is 4 times 4 minus 1 rotational symmetries. And that's true. And you can think about why that's true. Why are there 12 rotational symmetries of the tetrahedron? But yeah. Okay. So now let's construct complete regular maps with number theory. So this is a new, well, okay. So this is one of my main ideas here. So I want to construct complete regular maps using number theory somehow. So in genus 1, we can construct complete regular maps with number theory. Consider the ring of integer, the ring of Gaussian integers z adjoint I, which is just a plus bi, where a and b are integers. Inside of this ring, there's an ideal of index 5, the principal ideal generated by 1 plus 2i. So this is a set of elements in z adjoint I that are multiples of 1 plus 2i, and x ranges in the Gaussian integers. So this ideal has norm 1 plus, this ideal has index 5 because the norm of the generator, which is the product of the Galois conjugates, is 5. So 1 squared plus 2 squared is 5. So a fact from algebraic number theory, basic algebraic number theory, is that the index of an ideal inside of this ring is going to be the norm of the element that's generating this ideal. So here, the norm of this element is 5. So there are going to be 5 cosets of this ideal inside of z adjoint I. And moreover, the residue field, which is the field that you get when you take the quotient by this maximal ideal, is going to be the field with 5 elements. So z adjoint I modulo 1 plus 2i is the field with 5 elements. And this field with 5 elements is going to be the 5 vertices in my complete regular map. So let's see how to construct K5, the complete graph on 5 vertices embedded inside of sigma 1, the genus 1 surface, from the Gaussian integers. So first of all, we can obtain a torus sigma 1 by quotienting the complex plane by a lattice. So if I have a lattice, which is just a rank 2 free abelian group inside of the complex plane, then I can quotient out that lattice to get a torus. And note that the Gaussian integers z adjoin I is a square lattice in C. So I can draw this Gaussian integers set inside of here. So let's say this is C. Actually, I want a different color. So let's use black. So here I have C, and inside of C, I have the Gaussian integers z adjoin I. And the Gaussian integers look like the square lattice. So I have maybe 0, I, 1, 1 plus I, 2I. Yeah, okay. I'll just put in the whole or a bunch of points in this lattice. So this is my Gaussian integer lattice. So here's 0, this is 1, this is 2, 3, 4. This is I, 2I, and 3I. And inside of this square lattice, I have the ideal 1 plus 2I. So this is a sublattice of index 5, right? So inside of here, I have 1 plus 2I. And I will draw those in circles. So 1 plus 2I, here's another point on this lattice. And here's another point. And their sum is over here. Right. So that's a sublattice inside of this lattice, and this has index 5. So the elements of, okay, I'm going to consider the quotient C mod 1 plus 2I. So that's a torus. And I'm getting the torus by just identifying this side. Oops, let me try that again. So I have the fundamental domain for this index 5 sublattice is this square. Okay, so that's supposed to be a square. And inside of that fundamental domain, I have a bunch of points. And this fundamental domain, I need to identify this side with this side and this side with this side. And that's going to give me a torus. And that torus is going to be sigma 1. So that's my torus is going to be C mod by this index 5 sublattice inside of the Gaussian integers. So I have the square lattice, and then the elements of the residue field will be the 5 vertices of my complete graph on 5 vertices. So, right. So these 5 points, I have 1 point for 1 point, which is the equivalence class of these 5 points on the square. And then also in the interior of the fundamental domain, I have 4 points. And those will be the 5 vertices of a complete graph on 5 vertices. And the way I'm going to get the embedding, K5 embedded into this torus, is just, I'm going to have edges between just adjacent points in the Gaussian integer ring. So I state that in a different way, but basically these are my edges. So between any 2 points, I have an edge connecting them, and any point has 4 edges coming out of it. Okay. Right. So let's see. So here, maybe this is another point. This is another point. Okay, so I have these 4 points in the interior of my fundamental domain, and you see that every point is connected to every other point via some edge in this graph. Okay, so for example, this point represented by 1 is adjacent to 0, and it's adjacent to 2, and it's also adjacent to this point up here, and via this edge connecting to this point on the torus is also adjacent to here. So every vertex is adjacent to every other vertex, and there are 5 vertices in the graph. So this is an embedding of a complete graph on 5 vertices inside of the torus, and I've obtained it from this index 5 ideal inside of the Gaussian integers. And moreover, it's a regular map because it has many automorphisms coming from affine maps of the complex plane. To be more specific, the map z going to I to the k times z plus x for x in the Gaussian integers and k between 0 and 3 gives automorphisms of the map. And what this means is I'm just taking my point here and I'm rotating the plane by a multiple of 90 degrees, and then translating the plane to some other point. And that will be a valid automorphism of the map when you quotient by 1 plus 2i. And all of these automorphisms are going to permute the flags of this map transitively. So then you have a complete regular map. So this is my second example of a complete regular map. And the way we constructed it is by going through the Gaussian integers.
Or could I ask a question about the previous thing you did? So how do you pick 1 plus 2i and 3 plus I and 2 minus I again? These are the cosets, the representatives of the cosets?
Yeah, so I have this ideal 1 plus 2i, and maybe I'll go back.
Yes, okay.
Slide. Yeah, so this ideal 1 plus 2i is just the set of elements that are multiples of 1 plus 2i inside of the Gaussian integers. So basically, I have the square lattice, and then I dilate it by 1 plus 2i, and that gives me an index 5 sublattice. And so this point here, 1 plus 2i is just 1 plus 2i times 1. But then this point here is 1 plus 2i times negative I. And this point here is 1 plus 2i times 1 plus I.
Okay. Sorry, I guess I'm confused about why you picked those particular things. Is it just arbitrary or like?
So this is a fundamental domain for the quotient. So I'm quotienting out by this lattice, generated by 1 plus 2i. And now I'm showing you a picture of the fundamental domain for that.
Oh, okay, I see. So you pick like any fundamental domain and then you go with that.
Yeah, any fundamental domain is going to have 5 points. 5 points of the Gaussian integers when you consider them as equivalence classes, because 1 plus 2i is index 5 inside of the Gaussian integers.
So, and then sorry, you've got 4 points circled in red.
Yeah.
The 5th point is which one?
The 5th point is the equivalence class of these vertices of this fundamental domain.
Take the equivalence class of any corner. Okay, that's fine.
Mm-hmm. And the way I'm getting edges is rigorously, you can say it's just the image of an interval x to x plus I to the k. So they're just these, I'm connecting these things. Okay.
Yeah, thank you.
No problem. So we were able to construct a complete regular map K5 embedded inside of the torus using the Gaussian integers, Z join I. What about K7? And so we can leverage number theory again to get a complete regular map with underlying graph K7. And this time, instead of the Gaussian integers, let's consider the Eisenstein integers. So Z join omega is a set A plus B omega, where A and B are integers, and omega is a primitive third root of unity. So we can take omega to be e to the 2 pi I over 3, and it satisfies the polynomial omega squared plus omega plus 1 equals 0. Now inside of here, Well, let's look at the ideal 3 plus omega. So this again is the set of elements 3 plus omega times x, where x is an Eisenstein integer. And this ideal has norm 7 because the norm of the generator is the product of the Galois conjugates, which is 7. So you do multiplication, and it's going to be 9 times 3 plus omega squared plus 1. And omega plus omega squared is -1. So, okay. So this ideal, this principal ideal, which is a maximal ideal, has index 7. And so the residue field for this ideal is going to be the finite field with 7 elements. And now we can construct the complete graph on 7 vertices embedded inside of the torus from the Eisenstein integers in a very similar way as we did for the complete graph on 5 vertices. So what we'll do is we have the Eisenstein integers, Z adjoin omega, and inside of there we have the ideal 3 plus omega. And right, so let's do this. So the Eisenstein integers is a triangular lattice inside of the complex plane. So I'll draw some triangles. Okay, so I have some points in my Gaussian integer lattice, and then now the torus that I'm going to take is C modded out by 3 plus omega. And this is homeomorphic to a torus. So let me draw the fundamental domain for the ideal 3 plus omega. So I have 0 here, and then I have 1, 2, 3 plus omega, and so I also have inside of the ideal this point. Right. Or is it this point? No, that's not true. Yeah, it should not be that point. It should be this point. So I need to go 1, 2, 3 plus omega. But that's all rotated by omega squared. Okay, and then I also have the sum of these 2 points. So this is 0. This is 3 plus omega. This is what is this exactly? It's 1, 2, 3 minus or plus omega squared. Right? And then I have their sum, which should be so I can go 1, 2, 3 plus omega. Okay. And what point is this? This is 1, 2, 3, 4 minus omega. So it's not too important what the coordinates are, but this is a fundamental domain for my sublattice. And it's a parallelogram. And inside of it, you see there are 6 points in the interior. And I'm going to get a complete graph on 7 vertices by connecting these points using these edges like this. Right. And also need to have these edges. I think it comes here. And the last one. Okay, so that's the complete graph on 7 vertices embedded inside of a torus. And we got it from the Eisenstein integers. And just like before, it's a complete graph and it's a regular map. So it also has many automorphisms coming from affine maps of the complex plane. And this time z is going to map to omega to the k times z plus x. Okay, so yeah. So now we have 3 examples: the tetrahedron, the complete graph on 5 vertices embedded inside of the torus, and the complete graph on 7 vertices embedded inside of the torus. And the tetrahedron is just on the sphere, and it's the usual thing that we think of. But these two are interesting in that we obtained them by thinking about these rings, z join I and z join omega. And you might ask, what about K6? Does there exist a complete regular map with underlying graph, the complete graph on 6 vertices? And the answer is no, because Biggs proved any complete regular map must have underlying graph with the prime power number of vertices. So if you look back on all 3 of these examples, 4 is 2 squared, 5 is prime, and 7 is also prime. And Biggs did more. Not only did he prove that complete regular maps have an underlying graph with a prime power number of vertices, he also gave examples of complete regular maps for each prime power. So he constructed them as Kelly maps for the finite field. So in 1971, Biggs constructed complete regular maps, Kn embedded inside of sigma g, for any prime power n, p to the e, as Cayley maps associated to the finite field with n elements, or p to the e elements. So, is there a question?
We just joined in. I realized there was no half-hour margin this time. Or am I joining in too late? What's the hour there now?
I think I have until 4 to speak, right?
Yeah, it's 3:30 here.
Ah, I see. Okay.
Okay, so I won't get into the details of the scaling map, but the point is, okay, the basic idea is just you think of the finite field, the elements of the finite field as elements as vertices of your graph, and then you pick a primitive, a generator of the multiplicative group in the finite field, and the powers of that generator are going to tell you the cyclic ordering of the vertices around 0, and then you get the cyclic ordering around other vertices just by translating or adding to that. So, okay, so that's a quick idea of how to get Cayley maps from finite fields. And then James and Jones in 1985 proved that all complete regular maps are given by Biggs construction. So the only complete regular maps are those constructed by Biggs as Cayley maps associated to finite fields. And also the orientation preserving automorphism group of a complete regular map M, which is Kn embedded inside of sigma g, is isomorphic to the affine group on this finite field. So the orientation preserving automorphism group of a complete regular map is isomorphic to the affine group on this finite field, which is the set of transformations, linear transformations of this finite, not linear transformations, they're affine transformations of this finite field thought of as a one-dimensional vector space over itself. So they're the maps Z going to AZ plus B, whereas A is in the multiplicative group of the finite field and B is in the additive group of the finite field. And notice this affine group also has n times n minus 1 elements, which is where that fact I told you about the orientation preserving automorphism groups of a complete regular map comes from. So it seems like everything is understood about complete regular maps. And what else is there to understand? Like Biggs constructed all of them, essentially. And James and Jones classified all of them under Biggs as being what Biggs constructed. Okay, so what I want to understand are the connections to number theory. So to get into that, I need to talk about dessins and Riemann surfaces.
Can I ask a quick question about the Biggs construction?
Yes.
So is that for any G? I mean, any G, take any G, it contains all the prime powers, or
No.
for each prime you can find
For-
some G?
For each prime, there exists a unique G. And you can compute the genus in terms of, not for each prime power. So you can
So
compute
there's
the
a unique
genus.
G. Okay,
Yes.
thank you.
Yes. So you can write down a formula for that. And it's also the case that, so any complete regular map on n vertices has the same genus, but there can exist multiple complete regular maps with the same number of vertices on the same genus G surface as a topological surface. But James and Jones also understand how to go between those maps using what's called Wilson's map operators. But that's another topic. So basically, from the topological point of view, everything is understood. But I want to talk about dessins and Riemann surfaces. So let me start here. So a dessin is a bipartite graph where a bipartite graph is a graph where the vertices are colored one of two colors, and the edges only exist between vertices of different colors. So here's an example of a bipartite graph where the graphs are split into red vertices and blue vertices, and the edges are only between red and blue vertices. There are no edges between red vertices and no edges between blue vertices. And now a dessin is an embedding of a bipartite graph into a surface such that the complement of the image is a disjoint union of topological disks. And this is very similar to the definition of a map. A map is a typo, but a map is an embedding of a graph into a surface such that the complement of the image is a disjoint union of disks. And now to get a dessin, you just need to replace the map, the underlying graph with a bipartite graph. So here's an image of a dessin. It's a genus 2 surface, and inside of there, I've embedded a bipartite graph with black and white vertices. So this is an example of a dessin or dessin. I don't know how to pronounce it. It's French for drawing. And so given a map, we can obtain a dessin by taking the bipartification of the underlying graph and embedding that into the same surface. So here's the tetrahedron, which is a map on the sphere, and we get a dessin on the sphere by taking the bipartification of the underlying graph. And what that means is just adding new vertices at the midpoints of every edge. So now this tetrahedron, which is a map on the sphere, has become a dessin on the sphere. And now there's a way to equip the underlying surface of a dessin with the structure of a Riemann surface. And if you don't know, a Riemann surface is just a one-dimensional complex manifold, i.e. it's a surface with an atlas of charts there's a typo here again. A surface with an atlas of charts such that the transition functions are holomorphic, and a chart is a homeomorphism from an open subset of your surface to an open subset of C. So here's the genus 2 surface. It's a topological surface, and I have two charts, U1 and U2, get sent to subsets of C. And for this to be a Riemann surface, I need that the transition maps between subsets of C have to be holomorphic functions of subsets of C. So that's a Riemann surface. And what I'm saying is that given a dessin, which is just an embedding, it's just a topological notion, it's just an embedding of a bipartite graph into a surface, you can enhance the surface with the structure of a Riemann surface. So structure of a one-dimensional complex manifold. So I'm going to describe how to do that. So first, there's a step. You go from dessins to triangulations. And here, a triangulation means a triangulation of a surface is a collection of triangles that cover the surface, and such that the intersection of two triangles consists of a union of edges or vertices. So given a dessin, one obtains a triangulation by adding new vertices to the centers of faces and adding new edges between those face vertices and each of the black white vertices along the boundary of the face. So this is kind of wordy, but it's a simple idea. You just take your dessine and then add new vertices. So I'll draw that in red at the center of each face. So remember, a dessine is an embedding of a bipartite graph into a surface such that the complement of the image is a disjoint union of topological disks. Now I just put in red vertices at this at some interior point of each topological disk. And then I need to add in edges between these face vertices and each of the black and white vertices on the boundary of this face. So here I have all of these new edges coming in. Yeah. And this splits my surface into a bunch of triangles. And that's how you get a triangulation from the dessine. And remember, at the beginning of the talk, I said my surfaces are oriented. So the orientation of the underlying surface allows you to color each triangle black or white, depending on whether the triangle has white vertices and black vertices, like the cyclic ordering. So every triangle is going to have a vertex consisting of a white vertex, a black vertex, and a red vertex. So every triangle is going to look like a red, white, and black vertex, but the cyclic ordering can either be white, black, red, or it could be black, white, red. So depending on what ordering you have, given by the orientation of your underlying surface, color each triangle black or white. So it looks like from this picture, what we're doing is if your cyclic ordering is white, black, red, then you color your triangle white. And if your cyclic ordering is black, white, red, then you color your triangle black. Okay, so that's how you get a triangulation from a dessine. And then, okay, so this is, I should go here. So from triangulations, you get Bell-E functions. And I can explain what a Bell-E function in the process of telling you how to get one. So given a triangulation of a surface sigma coming from a dessine, one obtains a Bell-E function beta from sigma to the Riemann sphere by sending white vertices to 0, black vertices to 1, and face vertices to infinity, and also white triangles to the upper half plane, black triangles to the lower half plane, and edges of the triangulation to the real line union infinity. So this picture explains what's going on. Sigma is on the left, which is my underlying surface, and I've just zoomed into a small piece of the triangulation given by the dessine. So I have this face vertex labeled by X, and I have this white vertex and this black vertex, and they together determine a triangle, a white triangle. And the way this Bell-E function is working is that it's specifying a homeomorphism between this white triangle and the upper half plane inside of the Riemann sphere. And it sends the white vertex to 0, the black vertex to 1, and the face vertex to infinity. So here's another picture of the Riemann sphere. And the Riemann sphere has the real line in red over here. So this is 0, this is 1, this is -1, and infinity. And the red line is the real line. And I is in the upper half plane, and -I is in the lower half plane. So the upper hemisphere of the Riemann sphere is the upper half plane, and the lower hemisphere of the Riemann sphere is the lower half plane. And this is a picture of how I'm sending my triangles to the upper half plane and my black triangles to the lower half plane, and sending the edges of the triangulation to the real line union infinity. So basically, I have a triangulation, and then each triangle either gets sent to the upper half plane or the lower half plane of the Riemann sphere. And stitching all of these homeomorphisms together gives me a map from my topological surface sigma to the Riemann sphere. So that's the Belly function. And finally, from Belly functions, you get the Riemann surface structure on your underlying surface. So remember, my dessins is a embedding of a bipartite graph into a surface such that the complement of the image is a disjoint union of topological disks. And I showed you how to get a triangulation from the dessins and a Belly function from that triangulation. And now the Belly function tells you how to enhance the underlying surface of the dessins with the structure of a Riemann surface. So given the underlying surface, so we want to give the underlying surface exactly the Riemann surface structure that it needs to make the Belly function a holomorphic map between Riemann surfaces. Alternatively, you can restrict the Belly function to small open subsets of your surface to obtain an atlas of charts with holomorphic transition maps. But this second description is not quite true because the Belly function is not a homeomorphism near vertices of the dessins. So you need to do something else near vertices to get the charts. But aside from the vertices of the dessins, if you just restrict the Belly function to small enough neighborhoods, then those are your charts of your Riemann surface, and the transition maps are holomorphic. Okay, so this gives you a way to enhance your underlying surface to a Riemann surface. And to recap, what did we do? We started with a dessins, which is an embedding of a graph into a surface. So the dessins is an embedding of a bipartite graph into a surface. And then from that, we got a triangulation. So the triangulation of my surface. And then from that, I got my Belly function. This goes from the underlying surface to P1C. And then from that, I get my Riemann surface structure. And it's the structure that I want to put on on sigma, such that this Belly function becomes a holomorphic map between Riemann surfaces. Okay, so now this part of my talk, in the last 10 minutes, I guess, I want to talk about the rest, which is the algebraic side of Riemann surfaces. So first of all, I haven't prepared this in my slides, but I just want to say it. So Riemann surfaces are algebraic curves. So if you give me an equation, y squared equals x to the fourth minus 1, or something like this, an algebraic curve is just the solution set to a polynomial equation in two variables. And we can get a Riemann surface by considering the solutions to this polynomial equation.
Yeah, sorry to interrupt, but I mean, the real point about an algebraic curve is that it's one dimension. So you can take three variables and two equations, and you'll also usually get a algebraic curve. You know, one less equation than the number of variables will typically give you an algebraic curve.
Right. Okay. Thank you.
Yeah, it's not very important, but you know, just sorry.
Okay. Thank you. So right. So an algebraic curve is a one-dimensional variety determined by a set of polynomial equations. And then, so if you consider the complex solutions to those, to that set of polynomial equations, you get a Riemann surface. And it also turns out that given any Riemann surface sigma, you can compact connected Riemann surface, you can embed it into projective space such that the image of this embedding is going to be an algebraic curve. So I don't have.
with singularities. I mean, if you want to embed it in the plane, you have to allow for singularities.
Okay. Right. And then Bellier's theorem is saying that given the Riemann surfaces that come from dessins, so if I have a dessine, and then, so, okay, it's saying exactly this. So the algebraic curves defined over the algebraic integers are precisely those Riemann surfaces that you get from the dessins. Okay, so that's a very short version of Bellier's theorem. And so I have this question. I have these complete regular dessins coming from the bipartification of a complete regular map. So for example, K5 embedded inside of the torus, or K7 embedded inside of the torus. And then I take the bipartification of those to get what I'm calling complete regular dessins. And what I want to do is find affine models for these complete regular dessins. So I want algebraic equations, polynomials. I just want polynomial equations with algebraic integer coefficients. Such that, and also this the Belly function that I described before for dessins is going to be a rational function or a meromorphic function on my Riemann surface. And it can be expressed as a rational function on this algebraic curve. So I want to get these affine models for which are just the algebraic curve together with the Belly function. So here's the picture for the complete regular dessine of K5 embedded in the torus. So this picture here is the complex plot of the polynomial equation y squared equals 4 times x cubed minus x over 1 plus 2i to the fourth. And the embedded graph is the pre-image of the interval 0 to 1 under the rational map. Xy gets sent to 1 over 1 plus 2i to the 8th times x squared times the fourth power of 1 plus 2i to the fifth times x squared minus 1 over 1 plus 2i to the cubed times x squared minus 1. So this is the Belly function. And this is my underlying surface. And together, this is what's known as a Belly pair. And the dessine is the pre-image of the unit interval under this Belly function. So what you see plotted here is just the black lines are the pre-image of the interval 0 to 1 under this rational function. So yeah. Okay, so I want to share this picture in MATLAB. So let me share my screen. So switching over to here. Yeah. Actually, I want to share my whole screen. Okay. And so what you see here is the is just that exact polynomial equation. So this is a graph of the polynomial, and the black points are the pre-image of the unit interval under the Belly function. So let me move this around. And the blue points are the pre-image of 0, and the white points are the pre-image of 1, and the red points are the pre-image of infinity. And so you see there are 4 blue points here, and then there's 1 more blue point at infinity. So there are 5 blue points in total. And then between any 2 blue points, you have a black edge. So for example, I have one blue point over here, another blue point here, another blue point here, another blue point here, and then 1 more at infinity. And then between each of them, I have an edge, right? So every edge has 4 vertices, 4 edges. Every vertex has 4, every blue vertex has 4 black edges coming out of it. And the same situation is true for every other vertex, right? So this is the complete graph on 5 vertices embedded inside of this algebraic curve, which is an elliptic curve. So it's a genus 1 curve. And right, let me switch back to PowerPoint. Yeah, so that's that. And we can also write down coordinates for the graph, coordinates of the vertices, or the pre-image of 0, the pre-image of infinity, and the pre-image of 1. And so this is what I wanted to say. So these 2 pictures are the same picture. On the right, I have the complete regular map on 5 vertices. And on the left, I have the affine model for the dessins, for this specific, the bipartification of this complete regular map. Right. Okay, so I guess that's all I have time for. And yeah, so that's my talk. Thank you.
Thank you very much.
Thank you, Ajmain. It was a lovely talk. Let's see. Let me just. So can you end your screen share? Oh, excellent. So so I have a question. And actually, so I understand Grothendieck was fascinated by Bialy's theorem, but do you know what was his goal in introducing these children's drawings?
Yes, so Grothendieck was interested in the absolute Galois group, which is the Galois group of the algebraic integers as an extension of Q. And so there's an action of the absolute Galois group on dessins that you get by considering dessins as algebraic curves defined over the algebraic integers, and then acting on dessins just by acting on the coefficients of these defining polynomials, and also the coefficients of the Belle function as a rational function to the Riemann sphere. So this gives you an action of the absolute Galois group on dessins. And so you can understand this very complicated, or you can try to understand this very complicated absolute Galois group by trying to understand this action on these children's drawings.
But it's still the case that no one's constructed an element of that Galois group other than the identity and conjugation. Is that correct?
Well, I'm not sure. But people have tried to understand orbits of this action by drawing dessins and understanding their orbits and their fields of definition and so on. So this is, yeah, there's a lot of work going into this side of things.
Right. But Grothendieck never published anything other than his job application about this. Is that correct? Do you know?
Yeah, I think so. I think this was the last thing that he wrote before he left.
So what is your goal in studying all this?
Yeah, my goal is to, so basically, I just wanted to understand this Riemann surfaces are algebraic curves better, because I saw a proof of this in a book, and what it does is it tries to create like embed it into projective space by having enough meromorphic functions. So I thought that was cool, and then basically I'm just trying to do this for the complete regular dessins. Yeah, so I'm trying to obtain affine models for complete regular dessins.
So
And
how
I
far
got
have you
one.
gotten? How
Yeah,
far have you gotten?
Yeah, I've gotten so the one I showed you today is the K5 embedded inside of the torus, and that's the way I got that is by playing around with wire stress P functions, which I thought I was gonna mention today, but I didn't prepare that, and also ran out of time at the end. So
presumably you can do K7 as well, right?
yes, and using the same idea, like using a wire stress P function for the triangular lattice and trying to play around with that, you can, yes. So I'm pretty sure I can get an affine model for K7. And now
Both cases are elliptic curves with complex multiplication, right?
Exactly,
So that should
yes.
be, yes. Okay.
Yeah, so exactly. So it's a square lattice and a triangular lattice. And then for K11, this is the other one that I'm thinking about. And I have some ideas, but I'm still working on it. So yeah.
What's the genus in that case?
In that case, it's an embedding of the complete graph on 11 vertices inside of the genus 12 surface. But what you can do is you can take this genus 12 surface and mod out by the action of just sort of translations, or like you can send any face to any other face, right? So you just mod out by those, but every face has a rotational symmetry and like translational symmetries between faces. So just mod out by the translational symmetries. So you get a genus 2 surface when you take that quotient. And I sort of understand this middle surface, which is its polynomial equation of y squared equals x to the 5th minus 1. And then now you want to get a degree 11 unramified cover of this genus 2 curve. And yeah, I have some ideas how to get that using the Jacobian of the middle surface. So this is still work in progress. Yeah.
Great.
Nice.
Any other questions for our speaker?
Yeah, I guess I'm still kind of confused about why you'd want the affine model. Is it just for the sake of concreteness, or like you know what I mean? Like, why is it better than having the desin?
So it's really hard to get affine models, and it's just, yes, it's for concreteness. It's but it's also really cool, right? So like you're just drawing graphs on surfaces, and now this is an algebraic curve defined over the algebraic integers. What actually is that curve? What actually is defining polynomials, right? It's really hard to write down explicit examples.
Sure.
And I'm trying to do that, basically.
Yeah. By the way, like, excellent presentation of the dessins. Probably the best presentation I've ever seen of that in my life so far. So
Thank you.
Yeah, no problem. Yeah.
Any other questions for our speaker? I noticed Sandor just logged in, and I assume it's because of the fact that in Europe, you've switched out of daylight savings time. But in America, I think we do it this weekend.
That's why I interrupted at the halfway mark. I had forgotten, and then I was signing in the middle and thinking it should be the schmooze time. So
Right,
my apologies.
I think, is it this Sunday that we switch out of daylight savings time back to regular time?
Yes.
Yeah, because I know right now it's only a 4-hour difference to London, 5 hours to Paris, 5 or 6 to Budapest or to Hungary. I don't know. What is it to Israel? 7 hours? No, 6 hours probably.
6 hours, 6 hours, that's right.
But next
Okay,
week
I'd
it'll be
forgotten.
7 hours. Yeah. Okay. And next week our speaker is Laszlo Puth. I don't know how to pronounce it correctly. Sandor could correct me. From Hungary, who was one of the world's experts on Menon's identity. So someone knowledgeable will talk about it, which is great. So Ashmain, thank you again. That was a lovely talk.
Yes, thank you.
Thank you for having me.
Okay, everyone. Stay well.
If I may ask, what happened to last week's lecture?
What happened to it? What do you mean?
Yeah, I mean, we missed it, and then I went to look for it. I thought it's recorded, and I could
Oh.
not find it.
Maybe I forgot to upload it. I will double check.
Okay, my thanks.
And if I